Hello, welcome to my space station. Today we'll be exploring Schrödinger's cat and quantum entanglement in slightly more detail. So I did a video a while ago on Moore's law, and towards the end of it I discussed slightly about Schrödinger's cat. I recommend you go watch that video first because it will be pretty important in understanding this video. So let's get into it. So I gave the example of a cat being in a box in two states, either being alive or being dead. And also give the example of there being a radioactive isotope, which decay time is uncertain. It can be decayed or it cannot be. These two examples are very essential to understanding what the real theory of Schrödinger's cat is. So Erwin Schrödinger, as he put this, is there's a cat in a box and there is a radioactive isotope, right? Which decay time is uncertain. There is a chance it might decay in the next second, there's a chance it might decay in a longer time than that. So there's a sensor that senses if there's been a change in this jar in which the element is in, and that sensor would trigger a vial of poison, a very acidic poison, that would drop on the cat and that would kill the cat instantly. So the experiment basically assumes that the radioactive isotope is in a state of quantum superposition, and so is the cat. To an onlooker, right, the box is completely sealed, no odor can come out, no light can go in, no sound can come out. Basically, you're not aware of anything happening inside of the box. So let's say you put the cat in, and what is the chance of the cat being alive and what is the chance of the cat being dead if you check in the next 10 minutes? Now, because of the decay times of the radioactive isotope inside over there, the cat's life is uncertain. If the element decays within 10 minutes, then you would find the cat dead. If the element does not decay within 10 minutes, then you will find the cat alive. There's a 50% to 50% chance. And Erwin Schrödinger basically said that it makes sense to put these two probabilities together and to put the cat in a state of superposition. It's dead and it's alive at the same time. But you will never know until you actually open the box. So what's the application of this in today's modern world? Well, assuming the cat example, not very much. But if you apply this into things like quantum computing, it's very important. So here's when we get into quantum entanglement. Now, let's hit you with a fact. Teleportation is actually possible in this world. Okay, there are two types of teleportation. Teleportation of matter and teleportation of information. What we are mostly used to seeing in cartoons and anime is that a person just teleports, right? Just vanishes from one point, appears on the other point. Well, that is not possible. Teleportation of information, however, is possible. Now, how this happens is that, let's say there are two atoms, right? And one is positively charged and the other is negatively charged. And they both are in a state of quantum superposition. Now, that basically means that atom A could be positively charged, could be negatively charged, and atom B could be positively charged and could be negatively charged. We don't know. So, when two atoms are when they're entangled, quantum entanglement is happening, we know that there is a relationship between the outcome of the atom A and the outcome of atom B. So let's say the relationship that we know of is that if atom A is positive, then atom B has to be negative, right? So following this logic, we can, let's say, put one atom on Mercury and put one atom on take Neptune, right? So even though these atoms are millions of kilometers apart, right, we can still tell what atom B is by looking at the state of atom A. So let's say these both atoms are in like a concealed jar, you can't see inside of it. And let's say on Mercury, you open the jar, okay, and you see, inspect it, and that atom is in a positive state. Instantly, without having to do any experiments on atom B, following the logic that you had determined before, you would know in an instant that atom B is in a negative state. But since atom A is positive, atom B is negative. So again, what is the application of this? With this atom example, not very much. But when you get into when you get into quantum computing, this is very important. Now, I'll get into the details of how computers use this using quantum gates. Now, sorry, we used to the Boolean gates that I discussed in the previous video. They take electricity in bits in 1 or 0. Every wire carries one bit. So the thing with these, what I said, the quantum superposition and quantum entanglement, is that when you combine these two ideas, you make it so that an atom can be, like, you can transfer information from one side of the machine to the other instantly, and a single a single, like an atom, could carry one bit, but it could change the bit without having to be interfered by any logic gate. So basically, if you have one, like in electrical circuit, you have to put it to a NOT gate to get a zero. But in the quantum computers, it, like the atom is in both a one and a zero, so you don't need to mess with it, right? So how can this be applied? Well, we could send out these atoms to different quantum gates, and the outputs of these quantum gates, instead of having going through more atoms, could be instantly determined from the other side of the machine. Let's example, from the to the other side of the machine without having to go through there in the first place. Like if the quantum logic gate that has been done gives an output of 1, we can instantly travel to the other side. Let's say our logic is that if this is 1, then that is also 1. It retains the values. We can instantly start the second logic gate without having any wait time of traveling the atom in between. We can instantly start the other logic gate by 1. There, one input will be going in as 1. This reduces the computational complexity time, which I've talked about in the previous video of mine about P versus NP. You can watch that for more info. Basically, the computational complexity of time will go down as there is less time for the atom to travel between the logic gates, and so we could just infer what the state of one atom is from a different side of the machine. Now, this makes the computers very fast, and it's also pretty applicable in space, right? So, like when you're going on these space missions, you will obviously need very fast machines, right? And if not so on Earth, then in space you'll be useful, as you need to compute lots of different things like regarding the rocket, regarding the place to land, and also as AI is also advancing, maybe in the future AI will be used to power these rockets, not power, guide these rockets. And so in that way, the faster the AI is, the more safer the journeys to space will be. So I'll be continuing this video in a separate part later about how the quantum logic gates work. And this is all for this video. I hope you learned a bit about quantum entanglement and a little more detail about how Schrödinger's cat's theory works. So, like basically, this is a theory, right? It hasn't actually been proven that something can be in two states, but it makes sense to the point where people just go along with the idea, right? So that's a bit of information you must know. So that's it for today. I hope you enjoyed the video, and bye bye.